So, in the last class we have seen that the op amp has in its circuit basically a differential amplifier, and we have actually cascaded stages of differential amplifiers in the op amp, and what we get at the output of an op amp is a very high gain amplified signal, but the magnitude of this output signal is basically dependent on the two input signals that are being applied at the two terminals of the op amp, that is the inverting and non-inverting terminals. So, if the difference between the two signals applied at the two inputs of the op amp is high, then we get a high output voltage, but if the difference between the two input signals is less, then we get an attenuated output, and if the two signals are equal, then we are supposed to get a 0 output from the op amp. So, the output voltage of an op amp will be dependent basically upon the difference between the two input signals. For example, if we have Vi1 and Vi2 at the non-inverting and inverting terminals of an op amp, then the output voltage from the op amp will be highly amplified if these Vi1 and Vi2 are opposite, and if they are same, then it will be only slightly amplified, and ideally we are supposed to get 0 when they are equal or same voltages at the two terminals. So, the overall amplification or overall operation of an op amp is to reject the common signal and amplify the different signal. So, if we have the difference between the two signal higher, then we have an amplified output, and the common signal which is present at the two input terminals will be reduced to 0, and that is why if we consider the noise which is common to both the input signals being applied at the two input terminals of an op amp, so naturally the noise will be attenuated. That is one big advantage which we have in op amp, that the noise part in the two input terminals for the signals being applied will be attenuated or rejected, and the difference between the signals at the input terminals is amplified. Now, let us find out the output voltage when you have two input signals Vi1 and Vi2 at the two input terminals of the op amp. Now, these two signals in general, if we consider, they may be having both in phase and out of phase components. So, some portion of the two input signals may be common to both of them and some will be out of phase. So, the resulting output of the op amp, if we consider as V naught is the output voltage from the op amp, it is given by AD Vd plus AC Vc, where the AD term is denoting the differential gain of the amplifier and AC term is denoting the common mode gain of the amplifier. So, these two terms are very important when we consider the output voltage or amplified output. When we find out, these two play the role for finding out the magnitude, because as this AD is the differential gain and AC is the common mode gain, it will be, these two will be determining the output components which is arising because of the difference between the two signals and the common part of the two signals. So, the Vd voltage is denoting the difference voltage between the two signals. So, Vi1 and Vi2 we are applying. So, Vi1 minus Vi2, this is the difference between the two voltages, and the common voltage is denoted by Vc. So, Vc is the average between the two voltages. So, half of Vi1 and Vi2, half of Vi1 plus Vi2, that is the common signal or the common voltage between the two signals. So, then we have the output voltage given by this expression of V naught equal to AdVd plus AcVc. Now, the term which is very important in an op amp is common mode rejection ratio or CMRR. So, basically CMRR is the ratio between the magnitude of the two terms, as we have just now described, AD and AC, differential gain and common mode gain of the op amp. The ratio between the magnitude of the difference gain and the common mode gain of the op amp is known as CMRR or common mode rejection ratio. In absolute quantity, it is this expression, which is the ratio between the magnitudes of these two gains AD and AC, or it is also taken in logarithmic unit, that is log of CMRR is also taken. So, in that unit, logarithmic unit, it will be described as 20 log of magnitude AD by magnitude AC to the base 10. So, in these two ways it is expressed, CMRR is expressed. So, now we look back into that expression of the output voltage again. So, the output voltage AdVd plus AcVc, we do a little manipulation taking this AdVd term common. If we take AdVd common, then within bracket we get 1 plus AcVc by AdVd, then it can be written as AdVd into 1 plus AC by AD into Vc by Vd. The purpose of manipulating in this way is to introduce the term CMRR. So, that is further made equal to the expression AdVd into 1 plus. If we look into this term AC by AD, it is nothing but 1 by CMRR, because CMRR is equal to magnitude AD by magnitude AC. So, from this we get 1 by CMRR equal to magnitude AC by magnitude AD. So, we are replacing this AC by AD by 1 by CMRR into Vc by Vd. So, in this expression for the output voltage, if we observe closely, we find that if CMRR is very high, that is, the value of this common mode rejection ratio for an op amp is very high, then the output voltage V naught will be almost equal to AdVd, because this term being high means the overall term 1 by CMRR into Vc by Vd will be very small, approaching 0, because the denominator is very high. So, this whole term will be approaching 0. That means we are left with V naught equal to AdVd. So, that is a very significant analysis, because it tells that for a high CMRR op amp, output voltage is basically the gain, difference gain multiplied by the difference in the input voltages. So, the common mode part is almost rejected to 0. So, that is why we have to have a high CMRR op amp which will be amplifying the output signal based on the difference between the two input signals, and whatever a common part, it is almost equal to 0. So, now if we have an example, say for this example you are to determine the output voltage of an op amp for input voltages Vi1 is equal to 150 microvolt, Vi2 is equal to 140 microvolt. So, in this op amp, the two voltages which are applied at the non-inverting and inverting terminal. This is Vi1, this is Vi2. They have the magnitudes of 150 microvolt and 140 microvolt. Now, the amplifier has a differential gain AD 4000 and the value of the CMRR is given as 100. So, what is the output voltage that we have to find out? So, as per the description just now we have seen, V naught output voltage is given by the expression AD into VD within bracket 1 plus 1 by CMRR Vc by Vd. In this expression we can plug in the given values for the terms. So, what are the values given? Let us see, and these are Vi1 is given, Vi2 is given and the differential gain is given. Common mode gain is not given, but we know that CMRR value is 100. So, if we know the CMRR value and AD value, that is sufficient, because the CMRR is nothing but AD by AC. So, in order to find out the V naught, that is the output voltage, let us now plug in the values into this expression. So, AD is 4000, we know it. What is the VD, difference voltage? We can find out Vi1 minus Vi2, that is the difference voltage 150 minus 140, and that is 10 microvolt. So, 10 microvolt is the difference voltage applied between the two inputs of the op amp, and CMRR is 100 is given, and Vc and Vd we have found out. So, Vc we can find out because Vc is the common mode part of the two signals, and Vc is found out by average between the two signals, half of Vi1 plus Vi2, that is equal to half of 150 plus 140, both are in microvolt, and that gives the value of 145 microvolt is the common mode part of the two signals, and the difference component of the two signals we have found out to be 10 microvolt. So, we can find out now what will be the output voltage V naught. So, according to the expression which we know, AD into VD into 1 plus 1 by CMRR into Vc by Vd, every component of this expression we know now, we can plug in. So, what is AD? AD is equal to 4000. So, 4000 Vd we have found out to be equal to 10 microvolt. The units are written in microvolts. So, I need not repeatedly write the units, all are in microvolts are used. So, 1 plus 1 by CMRR is 100. So, 100 into Vc is 145, Vd is 10. So, simplifying this expression or finding out the numerical value, we now find out what will be this value, 4 into 10 to the power 4 within bracket terms, denominator is 1000, 145 by 1000 is 0.145. So, 1.145 into 4 into 10 to the power 4 gives the value of 45800 microvolt. To check this value, it should come for 45,800 microvolt, meaning it is equal to 45.8 millivolt. So, 45.8 millivolt output we obtain for this op amp having the two input signals which are 150 microvolt and 140 microvolt. Now, let us consider an ideal op amp. Now, when you call an op amp an ideal op amp, because if we consider an op amp circuit, what is inside that circuit is differential amplifier, but they are in stages. If we consider the op amp having input resistance, output resistance and its gain say A, then a simple circuit can be used to express that op amp or explain that op amp. Here it is a simple circuit having input voltage between these two terminals. This is say 1 1 dash, these are the input terminals, and the input voltage which is applied to the op amp is a difference input V1 minus V2. V1 and V2 are the two inputs at the two terminals of the op amp, non-inverting and inverting terminal. So, then the difference voltage will be Vd, which is equal to V1 minus V2, and the op amp will have an input resistance, and this input resistance is very, very high, and let us denote it by Ri. This Ri will be representing the input resistance. So, the input side is having these two parameters, one is the difference input, this is the input voltage, it has one parameter which is input resistance. And what will be the output of the op amp? Gain multiplied by the difference input, A into Vd. So, A into Vd is the voltage source at the output, meaning that we are getting an output voltage A times Vd, and this is the voltage source which is denoting that output voltage which we obtain at the output. But there is a output resistance also, although this value is very small, which we cannot ignore, which is R0. That R0 is the output resistance of the op amp. So, finally, what we get at the output, that is V0, which is AVD minus this drop occurring in the resistance R0. Practically, this is the circuit which is used to explain the op amp. We are basically having a simple circuit representing the op amp in terms of input resistance, output resistance, and the gain of the op amp. These are the parameters which practically we have in an op amp, which can be known from the data sheet available for an op amp also. So, in this circuit, it is the practical circuit of the op amp, but we will be now considering an ideal op amp where we will be considering that the input resistance Ri is infinite, output resistance R0 is 0, and the gain A is also infinite. So, the ideal op amp consideration is useful for analyzing the circuits having the op amp, and in our analytical expressions which we will be using, or our analysis of the op amp circuits, it is obtained simply or easily by considering the ideal op amp analysis. That is why we are imagining an ideal op amp having the requisites of the parameters with certain specifications, like as we have now told that Ri should be infinite, R0 should be 0. In this way, the parameters ideally, if these parameters, if they have certain values, we consider that op amp to be an ideal op amp, and in all our analysis from now onwards, we will be using ideal op amp analysis having these properties. So, what are the properties of the ideal op amp, or what are the parameter values it should have? One is that ideal op amp has the characteristics of first, input resistance Ri should be infinity, output resistance R0 should be 0, voltage gain should be infinite, and bandwidth should be infinity. Bandwidth means the characteristics of the op amp, like voltage gain, it should not change with very low or very high frequencies. That means, throughout the whole frequency range of application, the characteristics of the op amp should not change. For example, if voltage gain is A, it or infinity, it should be same for all the frequency, whole frequency range, because we have seen earlier in the case of transistors, transistor gain, voltage gain, if we consider for very low frequencies and very high frequencies, the gain drops off or reduces. Only in the mid band the gain becomes constant. So, that is not a constant gain, it is varying with frequency, and that type of analysis or that type of characteristics should not be there for this ideal op amp. So, ideal op amp will be having an infinite bandwidth, that is within that infinite frequency range the characteristics are same. That means, we are not having any change characteristic like change voltage gain. For frequency range infinite means practically for whole frequency range we are getting the same characteristic. That is that is why it is written that bandwidth is infinite. Now, perfect balance also is one important property which has to be obeyed by this op amp, that is V naught is equal to 0 when V 1 is equal to V 2. So, if we consider the op amp, one is non-inverting and one is inverting terminal, let us have these voltages at the inverting and non-inverting terminals V 1 and V 2. Now, if the output voltage is 0, V naught is equal to 0, V 1 must be equal to V 2, and that means that the perfect balance is there for the op amp. Now, this perfect balance will come only because the differential amplifier, which is the basic circuit inside the op amp, has the transistors which are perfectly matched. So, when the two transistors are perfectly matched or balanced, we do not have any unbalanced voltage, and that means when these two voltages V 1 and V 2 are equal, then there should not be any output voltage, that means output voltage should be 0. That is to be maintained for op amp, that is one criteria. And another criteria is that characteristics do not drift with temperature. Temperature should not have any effect on the characteristics change. That is, whatever characteristics we are getting for the op amp, maybe the voltage gain or other parameters, they will not be dependent on temperature. So, even if temperature changes, we should not have a varying characteristic. So, all these properties are to be satisfied for the op amp when we call that op amp to be ideal op amp. So, actually this ideal op amp considerations make our analysis very easier. So, if we consider ideal op amp now as I is infinity. So, let us consider this op amp having the non-inverting voltage V 1 and inverting terminal has a voltage V 2. Difference voltage is then V 1 minus V 2, that is the voltage between the two terminals. What is the voltage? V 1 minus V 2, that is the difference voltage V d, and output voltage is equal to V naught. Now, as this ideal op amp has the consideration or the parameter R I infinite, input resistance is infinity. So, if there is an input resistance here, suppose R I, and that is infinity. So, if R I is infinity, obviously there cannot be any current entering into the op amp. So, the first consequence of this R I being infinity has is that the current entering into an op amp is 0. So, this is an important inference which we will be using in all our further analysis. So, this is the first principle which you will have to use when analyzing an op amp circuit, that is ideal op amp consideration has the current entering into the op amp as 0. So, as there is no current entering into the op amp. Now, another characteristic of an ideal op amp is that gain is infinity. Now, if input voltage is the difference voltage V d, output voltage V naught, so this is the gain of the op amp, which is A. Now, as A is infinity for an ideal op amp and V naught is finite, V naught we are getting a finite voltage at the output. So, what will happen is that the V d value, V d is equal to what? V naught by A. So, V naught by A again becomes V naught by infinity, which is equal to 0. So, what it means that for ideal op amp, the difference voltage is 0, means V 1 minus V 2 is equal to 0, that means V 1 is equal to V 2. So, for the ideal op amp, the voltage at these two terminals, inverting and non-inverting, this is V 1, this is V 2, these two are equal, and these two principles of the op amp, that means one is the current entering into the op amp is 0 and V 1 is equal to V 2, will be extensively used in all our further analysis. We will be using these two and find out basically what we will be getting at the output voltage. So, remembering these two basic principles of ideal op amp, let us now consider some practical op amp circuits. So, the practical op amp circuits are those circuits which we very often use, and one very simplest application of op amp is inverting amplifier. So, what is there in an inverting amplifier? There is an op amp and we are applying a voltage V1 at the inverting terminal. Inverting terminal is this one which is having a negative symbol. We are having a voltage V1 and we are having resistance R1 here in the input side, and RF is the feedback resistance. It is called feedback because it is from the output to the input. So, RF is called feedback resistance. Now, this is the circuit of an inverting amplifier using the op amp. Now, what will be the output voltage V0? In order to find out the output voltage V0, now we will be using the properties of an ideal op amp. That means, we will be using the ideal op amp considerations. So, for all these analysis which we are going to do now, we will be following ideal op amp properties. So, the properties are mainly two. One is that there is no current entering the op amp and V1 equal to V2. V1 equal to V2 means the voltage at the inverting terminal is equal to voltage at this non-inverting terminal. But here we are applying a voltage at V1 which through a resistance R1 is connected to the non-inverting terminal. Now, we will be using the first principle that there is no current entering into the op amp because of the infinite input resistance. That means what? The current which is flowing from V1, let us name it by I1, this current cannot go and enter into op amp. So, where will it go? It will be following this path through RF. That means, the current coming from V1 it will be following through the path RF and it will not enter into op amp. So, if this is so, now we can very easily apply the Kirchhoff's voltage law and find out what is V0. So, that is what we are going to do. So, using the Kirchhoff's voltage law in this circuit, what is Kirchhoff's voltage law? This V1 minus I1 into R1 minus I1 into RF minus V0 equal to 0. So, we can write in another way also what is this loop. If we consider this loop V1 minus I1 R1 equal to 0, because this point and this point are same voltage and it is grounded. So, if I consider this loop, Kirchhoff's voltage law we can apply in this loop also. This is a closed loop. It is coming from plus terminal of V1 to ground and minus of the V1 is also grounded. So, this is a closed loop. So, this Kirchhoff's voltage law if we apply to this loop, it will become V1 minus I1 into R1 and there is no other drop, that is equal to 0, because this voltage is grounded, they are same voltage. Another voltage law, another loop is from starting from this say ground, we can go like this in the ground and we can go like this and complete the loop. That means, we can start our travel from the ground, then what will it be? It will be minus I1 into RF and then minus V1 equal to 0. So, there are two equations which we will be taking help of in order to find out V0. First is V1 minus I1 R1 0, that gives us an expression for I1 which is equal to V1 by R1. The other equation which we have written from this loop is 0. This is you can start from ground and write this voltage is 0. This is nothing but a ground voltage is 0 minus I1 RF minus V0 equal to 0. That is what. So, what is V0? Minus I1 into RF and minus I1 we can replace from here. So, I1 is V1 by R1. So, it becomes minus V1 by R1 into RF. So, V0 equal to minus V1 by R1 into RF. From that we get the gain V0 by V1, we can find out what is that gain. minus Rf by R1. So, this is the gain of an inverting amplifier using op amp. So, the inverting op amp circuit gives the gain minus Rf by R1, that is equal to V naught by V1, that is the inverting op amp. Now, if we consider a non-inverting amplifier, non-inverting, as the name suggests, the voltage will be applied to the non-inverting terminal, that is this plus terminal, it is denoting the non-inverting terminal. We are connecting a voltage signal V1, and here these two resistances R1 and Rf are connected like this. We are to find out the voltage V naught. So, in order to find out the voltage V naught, again same way we will be proceeding, and let us denote the current I by this current which is flowing in the RF, that is starting from this point. This direction you can choose in any way. Now, intuitively I am choosing the direction from right to left because this is the ground. So, it will be starting and ending at ground, it will be starting from here and ending at ground, but there is no hard and fast rule because we are choosing the direction of current, and we can choose it from left to right also, that is also will be giving you ultimately the same result, but I am just choosing the direction as like this from right to left. So, let us denote this current I which is flowing from this right point of RF to the left. So, it will be not entering the op amp, as we know that this is an ideal op amp analysis, current entering into op amp is 0. So, it is bound to flow in this direction to the ground. So, current direction is this way, same current will be flowing through R1 to ground because there is no current into the op amp. So, now we can use again Kirchhoff's voltage law. What will be Kirchhoff's voltage law in this loop? Starting from V naught minus I into Rf minus I into R1 equal to 0, because this current entering into the op amp is 0, and from that the expression for V naught is given as V naught equal to I into R1 plus Rf, because from this expression I get V naught minus I into R1 plus Rf, that I taken common equal to 0. So, we can write down the expression for I first. I is equal to V naught by R1 plus Rf, the current expression we have found out. Now, again we can come from V naught to the ground in this way also, that is another closed loop, and that loop, if we consider and apply Kirchhoff's voltage law, what we will be getting? V naught minus V1 equal to 0, but that is of course it will be not leading to a good expression, but what we will be using is, we will be using V naught minus I into Rf minus V1 is equal to 0. That means, we will be coming from, yes, from V naught we will be coming through Rf through V1 to ground. So, if we start from V naught, it will be V naught minus this drop I into Rf, and I am coming down, there is no voltage drop in between these portions because these two voltages are same. So, minus V1 equal to 0. So, that is this expression V naught minus I Rf minus V1 equal to 0. We have two expressions, one is for this loop, one is for this loop. So, the second loop we are getting the expression for V naught, that is that if we simplify V naught minus, now replacing I from the earlier expression, I is equal to V naught by R1 plus Rf into Rf minus V1 equal to 0, taking V naught common, 1 minus Rf by 1 plus R1 plus Rf equal to V1, transferring V1 to the right side. So, from this expression basically we get what is V naught, because V naught into, if this expression is simplified, it will be R1 by R1 plus Rf equal to V1. So, V naught equal to V1 into cross multiplying, we get V1 into R1 plus Rf by R1. So, finally, we get this expression of V naught equal to V1 into 1 plus Rf by R1. So, this is also a very important example of op amp application, which is non-inverting amplifier. Its output is given by the input voltage into 1 plus Rf by R1. So, this is for non-inverting. Earlier it was minus Rf by R1 was the gain for inverting op amp, and here the gain is 1 plus Rf by R1. Now, let us consider another application. What is this circuit? If you observe closely, now output voltage we will have to find out. What is this voltage? Now, this voltage is nothing but the voltage here. Again, this voltage is equal to the voltage here, and this voltage is nothing but V1, which is the applied voltage. So, V0 equal to nothing but V1, and that is generally known as a voltage follower. Means whatever input voltage you are applying, output voltage is the same, only it is used as a buffer. That means whatever input voltage we are giving, we are getting the same at the output. That is why it is called voltage follower, where output and input voltages are same. Now, let us consider another application where you can sum up the input voltages. Suppose we are having a number of input voltages given to the op amp, V1, V2, V3, etc. The output voltage now can sum up the input voltages V1, V2, V3, of course, in a scale manner. That means, the scaling will be there in terms of the resistances, not that V0 equal to simply V1 plus V2 plus V3, but it will be scaled with the resistances being applied, but properly choosing the resistances we can make it as an exact summer also. So, now in this application let us see, we are applying 3 voltages. For example, I am taking only 3 voltages, we can extend it to a number of voltages in the same way, that is the same principle is followed. So, here V1, V2, V3 are the voltages being applied at the input having resistances R1, R2, R3 and the feedback resistance is Rf. The plus or non-inverting terminal is grounded. Now, what will be the output voltage? We have to find out. So, in this type of circuits, it is always better to first of all follow from the first principle and name the currents flowing. If we name the currents flowing through the 3 resistances as I1, I2, I3, and the current in this Rf is say I, then what is I? If the current is here say I, the currents we are naming in the flowing in the 3 resistances say I1, I2, I3, then obviously as no current enters into the op amp, I must be equal to I1 plus I2 plus I3, the sum of all the currents that must flow through this Rf only, because they cannot go and enter into the op amp. So, that principle we will be applying. So, let us name the currents I1, I2, I3 which flow in the 3 resistances R1, R2 and R3, and the current which is flowing in Rf is, let us name it as I. So, the principle is that there is no current into the op amp, so I1 plus I2 plus I3 is equal to I. Now, we will be finding out what is I1, I2 and I3 individual currents. So, what is I? I equal to, if we look into the current I. So, applying Kirchhoff's voltage law, start from ground 0 minus, what is this I, the drop between these two is 0 minus V naught by Rf is equal to I. The potential drop between these 2 points, that is across the resistance, is 0 minus V naught, because this point is nothing but this point and this point is nothing but this point which is grounded. So, this voltage is 0. So, 0 minus V naught by Rf, that is I. And what is I naught? If we look into I1, what is I1? V1 minus 0 by R1, because this point is 0. So, V1 minus 0 or V1 by R1. What is I2? Similarly, V2 by R2. What is I3? V3 by R3. So, we get to the right side V1 by R1 plus V2 by R2 plus V3 by R3. So, now just simple manipulations we will be doing. So, minus V naught by Rf equal to V1 by R1 plus V2 by R2 plus V3 by R3. So, what is V naught? Cross multiplying with Rf minus Rf into this whole term. So, finally, we get V naught equal to minus Rf by R1 into V1 plus Rf by R2 into V2 plus Rf by R3 into V3. That is the expression for output voltage. it is like a summer, it is like summing up all the voltages V1, V2, V3. Of course, there is a minus sign in front because we are connecting at the inverting terminals, all these voltages. If we look here, all the voltages are in the connected into the inverting terminal. So, obviously, the minus sign will come as this phase will be out of phase or 180 degree out of phase. But if we look into the bracketed expression, it is like a summer, V1, V2 and V3 are summed up, of course, with a scale down version by the scaling by the resistances, means V1 will be multiplied by this ratio of Rf by R1, but properly choosing Rf, R1, R2 and R3, now we can get whatever we desire or whatever sum we desire. For example, I want to get V naught is equal to say minus 3 V1 plus 5 V2 plus 6 V3 etc. Some example if we take, then we can determine what should be the ratio between Rf and R1, Rf and R2 and Rf and R3, and properly choosing these resistances I can get the required sum. That is why it is called a summer. So, in analog computation, when summing up is required, imagine an analog computer where you are summing up the analog voltages, mind it, and that is done by this type of circuits. Now, another application which is an integrator circuit. We want to integrate a voltage. Now, integration, differentiation, these are the mathematical operations. If we want to perform by using analog computation, like here it is analog amplifier, we are considering not digital, we are considering an op-amp where the whole operations is analog. So, in analog computation, the summer, subtractor, integrator, differentiator etc. can be performed using op-amp, and IC op-amp IC 741 is an IC integrated circuit where you get this op-amp. And if we want to perform an integration operation on a signal, suppose I want to integrate V1 with respect to time, that I can do with a circuit like this where there will be a resistance and capacitance and they are connected to the op-amp. And if we want to find out V naught, given that the voltage V1 is applied at the inverting terminal and a resistance is there of course which is R, this capacitance is there across this op-amp which is C. Now, what will be V naught? In order to know what is V naught, now we will be using similar analysis the way in which we followed earlier. We will be naming the current, suppose input current I flowing from V1, it cannot enter into op-amp, so it will be flowing out through C, the same I. So, now if we apply Kirchhoff's voltage law, there will be two loops we can consider. So, first loop, if we consider this V1 minus I into R is equal to 0, that is one equation we get, and that is from that we get what is the value of I, that is equal to V1 by R. Now, again if we consider the other loop which is flowing from this ground, that will be 0 minus I into R minus V naught, 0 minus I into R minus V naught equal to 0. So, that is 0 minus I, no sorry, this is V1 minus IR is equal to 0, and the other is from here if we consider 0 minus the voltage across this capacitor is 1 by C integration I dt, 0 minus 1 by C integration I dt is the voltage across this capacitor. So, the voltage drop across this capacitor is 1 by C integration I dt. So, if I proceed from ground, apply Kirchhoff's voltage law, 0 minus 1 by C integration I dt minus V naught equal to 0. So, this is the equation. So, from here we get V naught which is equal to minus 1 by C integration I dt. Now, I can replace I which is equal to V1 by R. So, doing that we get minus 1 by C integration V1 by R into dt. So, what is V naught? Finally, V naught equal to we get R can be taken out, 1 by R can be taken out, it is outside the integral we can take out, it is a constant. So, minus 1 by RC into integration V1 dt, that is the value of V naught. It has out of phase because it is minus sign is there, of course, that means it will be out of phase with the V1 signal. But if we consider this expression of V naught, it is nothing but integration of V1 dt is there. So, we are integrating V1, basically we are getting an output which is integrating V1. Of course, there is this 1 by RC term is there, it will be scaled down by 1 by RC, but the nature of this voltage, it is an integrating the input voltage. So, that is the operation being performed by this connection of this op amp in such a way with RNC connected in this fashion that we finally obtain the integration operation. Similarly, we can get a differentiation operation. If we want to differentiate a voltage V1, say we want to differentiate, then the positions of R and C will be just interchanged. Here it was C here and R here, we will be interchanging C and R. C will be coming to the input and R will be across this op amp. Now, what will be the output voltage? Similarly proceeding, we will be getting by applying the Kirchhoff's voltage law again. What is this Kirchhoff's voltage law being applied? That is V1 minus the drop across this capacitance, that is this voltage drop across this capacitance is V1 by C integration I dt. So, V1 minus 1 by C integration I dt, V1 minus 1 by C integration I dt, you come down to ground, that is V1 minus 1 by C integration I dt, V1 minus 1 by C integration I dt equal to 0. This is one equation when you come to ground from starting from here. Another is you go in this direction, that will give you 0 minus I into R minus V naught equal to 0. So, this is the other equation. Now, just manipulating this equation a little, take the differentiation on both the sides, dV with respect to time, dV1 by dt equal to 1 by C. ddt of integration I dt means it will be simply freeing the term I. So, it will be 1 by C into I. So, what is I? C into dV1 by dt. From the second equation, we get what is V naught? 0 minus IR. Now, that is equal to minus I can be replaced from here, C into dV1 by dt into R. So, V is equal to minus RC dV1 dt. So, if we look into this expression, this is nothing but it is differentiating the voltage V1. So, we get a differentiation of the signal V1 by this connection of this op amp to the resistance and capacitance in this way, and in the earlier case we were getting a integration operation. So, these two are examples where the op amp is being used as in a circuit which will give you integration as well as differentiation. So, these mathematical operations can be performed by the op amp like that. Now, another example let us take, which will be showing how the subtraction operation can also be done. We have done addition, we have done integration, we have done differentiation with op amp. Now, subtraction or difference between signals can be found out. So, here the two signals being applied are V1 and V2, the resistances connected are R1 and R2. Now, if we now analyze the circuit, then we can first of all we just denote the node voltages which are at the nodes A and B, like we are just naming for our easy analysis, we will be naming the nodes A and B, that is the inverting and non-inverting terminal node voltages are denoted by V3, say, because we know V3, the voltage at node A is equal to voltage at node B, both the voltages are equal. So, let us name it as V3. Now, this V3 we are introducing just to easily analyze the circuit. Now, if we apply now the Kirchhoff's current law, because we are having the nodes, we can apply Kirchhoff's current law. What is Kirchhoff's current law? If we remember, the algebraic sum of currents at a node equal to 0. So, algebraic sum means plus and minus depending upon in what direction it will be. So, if we consider a node A we will be considering and we will be applying Kirchhoff's current law. So, what will be the Kirchhoff's current law being applied at node A? The incoming current, sum of incoming current equal to sum of outgoing currents. So, V1 minus V3 by R1, that is incoming this direction, and that V1 minus V3 by R1 must be equal to the, this is incoming, the outgoing is V3 minus V0 by R2. So, that is equal to V3 minus V0 by R2. This is applying Kirchhoff's current law at node A. Now, applying Kirchhoff's current law at node B, V2 minus V3 by R1, that is the incoming current, which is equal to outgoing current is which one? There cannot be current going into the op amp, because this is ideal op amp consideration. So, the current which will be coming out from terminal B, it is equal to V3 minus 0 by R2, because this point is grounded, that is equal to V3 minus 0 by R2 means V3 by R2. So, we get V2 minus V3 by R1 is equal to V3 by R2. These two are the key equations now which will be rearranged. Rearranging equation 1 conveniently, what we get is that taking the term V3 common. So, in equation 1 if we take V3 common, transferring to the other side this term, V3 take common, it will be 1 by R1 plus 1 by R2 and then minus V1 by R1, that is equal to V0 by R2. I am transferring this to the right side and the term having V0 by R2 to the left side. So, this is the equation 3 is the rearranged form of equation 1. Similarly, rearranging equation 2, I get take common V3 into 1 by R1 plus 1 by R2 minus V2 by R1 equal to 0. So, now if we look into the two equations 3 and 4, we can very easily get rid of the term V3 just by subtracting 4 from 3. If we subtract the equation 4 from equation 3, what will it be giving us? This two term will go, so it will be positive. So, we get V2 by R1 positive minus V1 by R1 equal to V0 by R2. So, from this we get what is V0? V0 cross multiplying by R2, we get V0 equal to R2 by R1 into V2 by V1. So, if we now observe this expression, what we get to see is that we are basically having a difference between the two voltages V1 and V2. So, V1 and V2 were the voltages which were applied, V2 were the voltage which was applied to the non-inverting terminal, V1 was the voltage applied to the inverting terminal. So, V2 minus V1, this algebraic difference is obtained at the output. Of course, it is multiplied by a factor R2 by R1, where R2 and R1 are the resistances which were connected in the circuit. So, now one thing is clear is that we can get this difference operation also from a circuit connecting the op amp properly with resistances. So, the factor R2 by R1 can be chosen. If we choose the values of R1 and R2 appropriately, then we can get what factor you want to multiply that difference, or even if you want to make R2 and R1 equal, that will be cancelling, we will be getting only the absolute difference, which is V2 minus V1 if R2 equal to R1. So, in this way we have seen that we can get a difference operation between two voltages also done. Now, let us do one example to sum up all the discussions today. This circuit, in this circuit you have to find the ratio between V1 and V0 and Vi or V1, that is the input voltage V1. So, V0 by V1, what will be that value? Given that the resistances are connected in such a fashion, this is R1 which is connected to V1, this is R2, this is also R. To analyze such a type of circuit, the easy way which we have been following, we will be still adopting the same way, naming the currents. So, input current let us name by I. This current is I, there cannot be any current into the op amp following ideal op amp consideration. So, current has to go in this direction, this current I has to go in this direction. So, I will be following in the direction through R. At this point, I am naming this voltage at this point as V. This voltage I am naming it for easy analysis, I am naming it as V. So, at this point the current will be divided into two parts. One will be going through the R to ground downwards, which is say I1, I am naming it, and the other is I0, which is flowing through R2. So, there are divisions of current at this point. So, now the application of the Kirchhoff's current law or voltage law, whichever is suiting, we will be now getting to know what is V0. So, following in that way. Now, what is the current I naught? We can write down that I naught current is equal to I minus I1, that is current division is taking place. So, let us find out what is I naught. I naught is equal to I minus I1. What is I1? What is I and what is I1? From here I can see what is I. I is nothing but V1 by R1. So, V1 by R1 is I, because it is it is this N voltage is 0. So, V1 minus 0 by R1, that is I. What is I1? V minus 0 by R or V by R. So, replacing this Vi by R1, Vi input voltage, let us take it as Vi. So, I am naming it as Vi, because this analysis I am doing with Vi. So, Vi by R1 minus V by R, that is equal to I naught, and that is equal to Vi by R1 minus. Now, what is V? If we see what is V, V can be found out if we start from 0, 0 minus I into R is equal to V. So, as 0 minus I into R is equal to V, because that is evident from Kirchhoff's voltage law being applied like this, from this terminal 0 minus I into R is equal to V. So, V is nothing but minus IR. So, replacing this V by minus IR divided by R is already there, what we get is equal to V1 by R1 plus minus minus plus, these are cancelled. So, V1 by Vi by R1 plus I we get. Again we can write that equal to Vi by R1 plus this I is nothing but Vi by R1. We have already seen that. So, replacing this I1 by Vi by R1, what we get? This is 2 times Vi by R1 is the expression for I naught. Now, what is V naught? We can write down V naught as V minus I naught into R2. V voltage here minus this drop equal to V naught. So, V naught equal to V minus I naught into R2. What is V? Minus IR we are replacing, minus what is I naught? We have found out 2 times Vi into R2 by R1. This I naught I am replacing by 2 times Vi by R1 into R2. So, that gives us, again I can be written as I is nothing but Vi by R1 into R minus 2 times Vi R2 by R1, or simplifying this expression I get V naught equal to minus Vi taking common, we get minus Vi by R1 taking common, we get R plus 2 times R2. So, if we find the ratio between V naught and Vi that is required, V naught by Vi is required, we get V naught by Vi equal to minus R plus 2 R2 divided by R1. So, now this expression is in terms of the resistances which are connected in the circuit, and we have got that the ratio between the output and input voltage equal to minus into the resistances R plus 2 R2 by R1. These resistances which are connected in this circuit, we are taking these resistance values as this is R, this is R, this is R1 and this is R2. So, now if we choose particular values of these resistances, actual values which we will be using, it will be giving say 1K, 2K etc., whatever values we get, we apply, then your voltage ratio will be in terms of those values, because you can see here if all are equal, suppose R is equal to R1 equal to R2. So, what we will be getting? Minus R plus 2R divided by R, and that is equal to minus 3R by R. So, minus 3. So, V naught by Vi becomes minus 3. That means, output voltage will be minus 3 times the input voltage. It will be out of phase with the input voltage and it will be amplified 3 times. If we have a signal which is 1 millivolt, we will be getting 3 millivolt, but minus, that is out of phase with the input voltage. So, properly choosing these resistance values, whatever we are connecting in this circuit, this is a typical circuit where the ratio between these two voltages, that is output and input voltage, will be determined by the values of the resistances which you are connecting. So, properly choosing these resistance values in terms of what you want to get, how much ratio between the two voltages you want to get, in that way you will be choosing these resistances. For example, just I have shown that if we want to get output voltage to be 3 times the input voltage, with a, of course, it is a minus, with a minus sign, because we are connecting the voltage at the inverting terminal. So, we will have to choose all resistances equal, that will give you 3 times. In this way you can choose the resistance values and you can find whatever required output voltage you want in comparison with the input, how many times you want it to be greater. So, in today's discussion we have seen basically the ideal op amp characteristics or properties of an ideal op amp, that it should have infinite input resistance and voltage gain should be also infinite, and we have used these properties extensively in finding out the output voltages for different various types of applications, practical op amp applications we have seen, starting from inverting, non-inverting op amps up to summing or difference amplifiers, also integrator, differentiator, etc. So, in all these practical op amp applications, we have used the ideal op amp analysis and we have used the principle of an ideal op amp, that input current in entering into an op amp is 0 and the gain is infinite. That is why the two voltages at the input terminals, that is negative and positive terminals, these two voltages are equal. These analysis we have extensively used. So, the analog computation can be performed using an op amp in a proper combination of resistances as well as capacitors, and we can get the different analog computation starting from summing, difference up to integration, differentiation, etc. So, this is the versatility of op amp which gives us analog computation.